Hello, so it's 11:30 p.m. and I'm trying to record a video of me doing the problem set. Now, full disclosure, I already did the problem set, so this is actually just me rehashing it. I'm going to try not to look at my notes and try to do it as organically as possible, but if I do, I will resort to my notes because I want to sleep at some point. However, this also allows me to commentary and think about things I did wrong or things I could have done better, so that would be pretty useful. I actually tried to record this video a while ago and I forgot to turn off the not disturb, and so texts started coming in, so I'm going to do that again because one-shot video making is the best video making. Anyways, so here's my desktop. Let's pull up a copy of Emacs. Let's pull up a copy of the problems, and now I'll turn on some speedrunning music and let's get to it. So the overall gist of these problems is basically trying to get us to find these things dA, which is essentially equal to, like, as we say here, like square root of 1 plus dot 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 dv. Right, it's essentially given some volume, there's a correction factor which will end up the dA. So then every single integral has the literal shape of integral of dA. Like that is every single integral in this whole problem set, just integral of dA. However, of course, I'm just not going to write that. I'm just going to figure out this and add up the differential area. But the point is that we're essentially just adding up the area. We're not scaling it by the function. This actually becomes important for the first problem. And we'll go from there. Anyway, enough talking. Let's get to it. So here's a rectangle. The area should be 5 times 7. That's what? 35? What's 5 times 7? 35. Yes. Okay, good. And even if the problem is 0, this 0 doesn't actually get multiplied anywhere because remember, we're only adding up dA, not the function itself. So for posterity's sake, let's just plot what it looks like. It's a function at 0. So let's plot the function. The x bound is 0 to 5. The y bound is 0 to 7. And so yeah, I mean, unsurprisingly, it's really flat and really sad. Taking a picture for posterity's sake and paste it in right there. Okay, cool. So, figuring out the correction factor dA is pretty easy. It's 1 because derivative of the partials of x and y of 0 are both 0. Square root of 1, as we all know, is 1. And so then finally, the integral is just integral over the volume of 1 dv, which also is just equal to the integral from the bounds dx dy, integral from, in this case, let's see, 0 to 5, 0 to 7, dx dy, and that indeed is 5 times 7, that's 35. Okay, so this one is shockingly bland, but I mean, all you're doing is adding up the differential area of 1d, which is 1, and 1 times dv is 1 dv, and that's just 5 times 7 given 2 bounds, so nothing special there. That's the first problem. Okay, moving on. And then it gets more interesting, which is we have the next problem, which is something with an actual correction factor to be accounted for. So I guess the area again of a plane, but this time is a more interesting plane, which is nice. So let's see here. So 2 times x plus 3 times y plus 10, plot 3D of f. And again, the same bounds. In fact, I'm going to recycle this line because that's better. And oh boy. So it's a pretty tall shape. Looks kind of like that. We can paste it into the figure. Very nice. And yeah, same drill goes from here. Let's look at this function. So again, the correction factor is in this shape. We derived it in class. I'm not going to derive it again. But fundamentally what this is saying is this is the dx dy is factored out. but all you're doing is finding the three-dimensional Pythagorean theorem on each of the ends and adding them up. You're actually realistically dividing by dx dy squared to get it to look like this, but fundamentally you just get that as your correction factor. So solving for what actual dA is here is the square root, so we all are given here is the square root of 1 plus left parentheses, right parentheses, copy this once again, and these both things squared of the fraction of partial f partial y. Oh, whoops. So we're gonna copy this, move that right there. Yep, ta-da. So it's this expression, which we know to be the square root of 1 plus, let's see. Taking a look at this statement, by x, these two terms are all constant, that would be like a 2 squared plus like a 3 squared, which is 4 plus 9, that's 10 plus 4, that's 14. Nice. So you'll realize that this is, again, a very nice correction factor, which is that dA is just 14. Whoops, forgot to add a dV onto each of those things. And therefore, taking the integral about dA, we can just actually copy these lines. It's just the same thing, except instead of scaling by 1, is scaling by the square root of 14. So this problem, very blandly, is just 35 scaled by the square root of 14. And yeah, that's pretty boring. Moving on. We have a parabola, which is much more interesting as a shape. I believe, if I'm not wrong, this is where it gets rapidly manually differentiable. Yes, indeed. Because the derivative of x squared is 2x, which means that you have to do trig sub, which upon Andrew's permission, I'm not going to bother to do here, and therefore we're not going to do the trig sub. Instead, we're going to ask Sage to take the integral for us, but we're going to set up the integral. So again, recycling the plotting lines. Whoa, fancy. So you can see it goes kind of way up. Given its curviness, I'm expecting that this to be slightly higher of a number than that. And then I guess we can find out what number it is. So. We're going to do the same thing again from the top. So copy this statement down there. By the way, usually I would be not like I would usually not be talking at the camera. Instead, I would usually be like saying these words. So you can see what I'm saying to you right now with my mouth is what I would usually write onto the piece of paper. But given I'm saying it here, I'm just gonna sort of talk at you instead, which is nice. Anyway, the first line remains the same. The second line we can see derivative of x is 2x, and then we're gonna put a square on that. And looks like 2x squared, well that would be 4x squared, if I know math, which I don't really. So yeah, so looking at this problem, by the way, just a quick side tangent pause thing. You can see the 1 plus 4x squared, the x squared term, and the 4 means that the right thing being squared means that it's kind of ripe for a trig substitution. And because it's a 1 plus something relationship, that's probably a tan x substitution. But we're not going to actually do the trig sub because I believe we'll end up needing integration by parts by splitting it into halves. But instead, we're just going to set up the integral and ask our lovely robot thing to do it for us. So we know that this is dA already, so we're going to paste that in there. So we are trying to take 1 plus 4x squared dV. And then with the bounds actually filled in, we have this. At which point we will promptly give up and ask Sage to do it for us. So we have the square root of 1 plus 4x squared. And then we want to f dot integrate. This is... did I have the bounds written backwards? Yeah, it's 5 comma 7. Okay, all of these have the bounds written backwards. That's very exciting. If you notice, I'm putting this line, this right here is just a small space because I really hate it when it says like dx dy. In fact, I'm going to endeavor to do that right again right here. So sometimes if I want my space to show, I'll just put a line slash and a space after that, which is pretty nice. Anyways, so we're going to integrate along y to 0 to 7. And then integrate along x from 0 to 5. And it looks like this. Hey, it's arcsine h. So this is the result that Sage gives. So we're gonna put that down there. For those of you taking the AP, if you ever do this, be sure to write the words using technology here. Using technology. Because I think they dock you points if you don't. So yeah, do that. That's a bit of an AP advice for y'all doing that right out there. Anyway, just reformatting these fractions so that they look nice. Epic. So, ooh. Okay, better, much better. So no, just so that we actually go do the sanity check, this top thing, which is 35 square root of 14, is, let's see, Sage 35 times square root of 14 is, oh, whoops, float, is 130, and this is, well, 181. Hey! So you can see the flat, like the curvy thing is slightly larger because it has more area to go through under that, which is what we expected from the beginning. So that's nice that we confirmed what we have. Okay, last problem. So hyperbolic paraboloid. This one, because it seemed like it was the most fun, I decided to parameterize. So yeah, let's go ahead and parameterize this one. Turns out it's actually shockingly the same if you parameterize it. You'll end up with just a worse way of finding the correction factor that takes longer, but it works anyway. So if you take this shape thing, put that in there, x squared minus y squared, and endeavor to plot it, you can see you have this much more interesting shape, which we'll take a screenshot of. See, this is something that's annoying. So, total side tangent. I have these keybinds, and they switch desktops. They're Alt 1, Alt 2, Alt 3, right? They switch desktops. I usually put Emacs on the third one, and I forgot that Emacs is on the second one, so each time you see me switch a screen, you'll see me switching to screen 1, switching to screen 3, expecting Emacs to be there, it not being there, and then switching to screen 2. Anyway, that's just a quick side tangent thing, which I'm annoyed about today. Anyways, cool. All right, let's parameterize this one. There is a stupid way of parameterizing this function, and then there's a smart way of parameterizing this function. Because it's like, what, 11 p.m., I'm endeavoring to do a stupid thing, which is far better. No, I'm just kidding. But the stupid way, this is a much more intuitive way of doing it, and it ends up working out as well. Quick side note, when I think about this problem, I use sort of the Leonard IJK circle thing. So when you're taking a cross product, in general, this circle will be pretty helpful in just a second. But to facilitate, this is just motivating, right? To facilitate the use of this circle though, what we have to do is we have to actually not write it in a vector, but use the three standard basis vectors of R3, which is hat I, hat j, hat k. And that corresponds to the vectors of 1, 0, 0, 0, 1, 0, and 0, 0, 1. Yeah, so these are the same thing, which means that if you add something scaled by I plus something scaled by j plus something scaled by k, you can think about that as putting the first element scaled by I in the first slot, putting the second element, etc., etc. But the added benefit of this is that now when you scale ijk by those things, it looks like a flat algebraic equation, which is less scary, and whenever things are less scary, you have more fun. So let's parameterize this. We're going to use a parameterization vector v of x of y that looks like this. Are you ready for the stupidest thing ever? X hat of I plus y hat of j plus x squared minus y squared hat of k. So you can see this is literally saying the x component is the x, the y component is the y, and the function is the z, which is kind of what a function means, but nonetheless it works. So jogging our memory back, we remember that the differential area is partial b partial t cross partial b partial s dt ds added up, and that is proven by the other Canadian guy, which we watched, which I think he's Canadian. I don't know. So yeah, let's do it. So let's find the partials of this expression first. So partial vec v partial x. Well, there's literally one thing that has, well, no, there's two things that has an x in it. So first of all, again, remember ijk, these are considered constants, so you have hat I plus 2x hat k, right? Hope that makes sense. So you can think about these ijk things as literal constants, just like c or any other constant. So x of I dx is the derivative of f of x is equal to x of I by x is just I, because I is a constant. Same thing here, we factor out the k from the derivative operation and take the thing in the middle. The negative y squared goes to 0, and then the derivative at 2x. Same logic goes here, we have partial x partial y, we get j minus a 2x 2y of k. Because again, left side goes away, middle side becomes j, and the right side becomes negative. Cool. Awesome. So now we are to cross product them together. So thing to know about cross products is that they distribute across multiple, so in this case, what we're trying to figure out is what these two things cross together are. Trying to figure out what this times is the cross product thing in LaTeX, and it always really annoys me, but that's okay. We're trying to figure out what this is. Eventually we'll need to figure out the magnitude of this, but bear with us. So because of the fact that cross products distribute, we can do a little bit of distribution, which is nice. We just have to remember what to distribute. So let's write that there. Excellent. So now with this expression, we can actually do the foiling. So first times first, outer times outer, inner times inner, and of course our favorite, last times last. Now see, when you do this, it's vitally important that the order is correct. So you can see first times first, ij, because again, cross products are not commutative. Outer times outer, ik, so outer times outer is I and k, yep, that's right there. Inner times inner is k and j, ooh. Got that order wrong. Right, addition and subtractions are internally commutative, but the cross product operation isn't. So you want to make sure that inside each of these terms, the order of things is correct. And again, k times k, fantastic. Okay. So now, we need to remember a few things, which is that the cross product is the perpendicularity of a vector onto itself. What that means is that if you take the cross product of this and that, it's projecting the vertical component, the sine theta component, down. What that also means is that you have two parallel things, they have no perpendicularity. Therefore, k times k, the standard basis vectors both pointing up, will be a very lovely 0. And that has just saved us quite a bit of work. Awesome. So now, for the rest of these cross products, the thing you want to do is to think about it as a circle. And because we're right-handed, we're going to use this one. I cross j is k, k cross I is j, I cross j is k, j cross k is I. Simple. If you go backwards, I cross k is negative j, j cross I is negative k, I cross k is negative j, so on and so forth. So just the ijk clockwise circle, your beautiful friend. So then, I cross j is k. K cross j, well, that's going backwards, is negative I. And I cross k, that's going backwards again, is positive j. Actually, let's put the j right there. Awesome. Okay. So, give me a moment to make sure I didn't screw up. I didn't. Actually, no, maybe I did. No, I didn't. Great. I didn't screw up. Fantastic. So, if you want to write it out in vector form now, I didn't do it in my actual submission, but you can still remember, again, I, j, k are the standard basis vectors. So this looks like the I component is negative 2x, 2y is the j component, and then 1 is in the k component, which is nice. According to this formula, then we're asked to take the magnitude of this vector, and in case you forgot what the magnitude is, it is simply the square of each of the components and the square root of that. So then we're going to endeavor to do this lovely thing. Square root of 1, well, that would be 1. Square root of 2x, then that will be positive 4x squared. And square root of 2y, well, that would be positive 4y squared. And that looks like, and that dx dy is what we have as dA. Now, we just spent a whole lot of work to end up with the visual confirmation of this. So if you think about this, 1 plus, we got the 1 plus, 2x squared, well, that would be 2x squared, that would be 4x squared, 2y squared, that would be 4y squared, which means that the parameterization equals to what we have up here. And in fact, total side tangent, if you want to prove the thing on top, you can also use the Canadian guy's proof for this thing and just apply this and do what we just did and abstract to end up with the thing on the top. Anyway, time to do basically the same thing yet again, which is we're going to paste this expression from the top downwards and put this correction factor we determined inside there again, and then again promptly give up and ask a calculator. Okay, that's reasonably silly as a result, so we're gonna ask for a floating point representation, which is approximately 326, and that indeed is larger than what we had on top, which I think it was 160 something. So you can see the even curvier shape than the curvier shape is even curvier in that it's floating up and therefore has a larger surface area. Okay, those are the problems. They're not written up as nicely as my actual solutions because my actual solution doesn't require me talking to a camera, but actually in my actual solution I explained essentially the same set of things as I did here. Okay, hope you had fun watching me do this. Hope you learned something, and if you didn't, well, I guess find me. It's 12 p.m. I should go to bed. It's 12 a.m. I should go to bed. Good night.